All right, so we've been lecturing on a little organic chemistry. We talked about alkanes and the first 10 alkanes. And again, as we talked about, everything sort of falls back to these guys, a lot of the naming and everything. So really good to know those. We talked about some different ways to write formulas, remembering again that we'd use our line structure a lot. And these are, again, our carbons through here. So we're going to get into, I think, and we'll come back to where we left off on the last part of the lecture. We'll come back to that in just a second here. But let's talk a little about naming alkanes, especially. So when we talk about naming, and especially organic naming, frankly, there's a lot of different names for organic compounds. There is sort of the official name, if you will, which is sometimes referred to as the IUPAC, the International Union of Pure and Applied Chemistry. They are the ones that come up with all these weird rules of why you name things a certain way. So that's usually the name that in most cases you go with in organic chemistry. But there are a lot of organic molecules that go by sort of historical names. They'll also go by common names. So it is not surprising to see an organic molecule that has like 3 different names for the same thing. For example, you could have something like this, which is it's an alcohol because it has that OH group. It is 2-propanol, which is the IUPAC name. It's also isopropyl alcohol, and it's also rubbing alcohol, so it's all the same thing. So it's also called by all 3 of those names a lot of times by different people. So in organic chemistry, there's just a lot of things that have just common names and regular names. But most of the time, the IUPAC name is sort of the way of going, and that's where we're going to sort of talk about the sort of steps to follow when you do IUPAC naming. So really, it all starts with the longest part of the chain. And what that means is you're looking to figure out the longest continuous carbon chain. Now, that doesn't mean it has to be the straightest carbon chain. It could go straight, it could go up, it could go over, or whichever way. But you're looking for the longest continuous carbon chain. That's going to be really like the base of your name. Then we want to figure out what is not part of the longest carbon chain. Those are what are considered groups. So you want really the longest carbon chain. Then you want to figure out what are your groups attached. So what are groups? So let's just take a moment here and maybe talk about what groups are. And groups can be what are sometimes referred to as alkyl groups. And these are essentially carbon-based groups that are not part of the main chain. So what are we talking about that? Let's see if we could just look at one here. Let's actually look at the one that we were talking about earlier there that we stopped. So we had something like this, I think. So if we were going to sort of go about naming both of these guys, the first thing that we would want to do is figure out the longest continuous carbon chain. Now, the guy on the left is pretty simple. It is just straight across, which is 4 carbons in a row. There is nothing else there other than the 4 carbons in a row. And we already know that 4 carbons in a row, all single bonded. That name is butane. Now, when we go to the guy on the right here, the longest carbon chain is how many carbons? It is 3. And you could get 3 by going straight. You could also, by the way, get 3 by going straight and then up. When you are counting the longest carbon chain, The only rule is you cannot backtrack. So you got to go in one direction until you hit a dead end, but you can't backtrack over something. So you could actually get 3 in several different ways. Now, it really doesn't matter which way you choose. I would recommend, though, if you do have sort of the straight part here, take the straightest one as your longest carbon chain. So when we go about naming this, because our longest carbon chain is actually only 3 carbons, which is this part, that is really the main part of our molecule. And what we know is 3 carbons is our friend propane, right? From our first 10 alkanes. Now, when we look at this, there is another carbon guy over here. It is not part of the main chain. This is what is referred to as being a group. More specifically, in this case, this is what is referred to as being a alkyl group, which basically just means it's a carbon-based group. Now, groups that are not part of the main chain are also based off of the alkanes, except for a difference. In this particular case, this has 1 carbon, which is based off of our 1 carbon alkane, which is methane. But this does not have 4 hydrogens. It actually only has 3 hydrogens. And the reason it only has 3 hydrogens is where the 4th hydrogen would be, that's going to give it the place to attach. And if you kept the 4 hydrogens on it, it would have too many bonds to it. So it basically will have 1 less hydrogen than the alkane. And because this is an alkyl group, surprisingly enough, it ends in YL instead of methane. This is what is known as a methyl group. And it basically has 1 less hydrogen than the alkane to allow it to connect. Questions on that? So we do have a methyl group here. And when we are naming things in organic chemistry, it's really all about telling a person where you can find everything pretty much. So it's all about location, location, location. So when we find the longest carbon chain, what we want to do is after we identify sort of the groups that are attached there, we actually want to number the longest carbon chain. Now, when you number the longest carbon chain, you basically have 2 options. I guess you could go left to right or right to left. So if we went left to right in this case, this would be carbon 1, this would be carbon 2, this would be carbon 3. If we went right to left in this case, this would be carbon 1, this would be carbon 2, this would be carbon 3. When we number the longest carbon chain, in the case of alkanes, it is the groups that should get the smallest number. Now, in this particular case, it actually does not matter which way I go. That group is always going to be at carbon number 2 in this case. So what that means is this is what is known as a 2-methyl because it's at carbon number 2 on the chain. And once you got everybody there, what is left to do is name the groups first in alphabetical order, regardless of prefix. So kind of like what we did with the transition metals, complex ions, no prefix. So this would be known as 2-methyl propane in this case. A couple of other things that we do is anytime we go from a number to a letter, we put a dash. Anytime we go from a letter to a number, we also put a dash. And if you happen to have 2 numbers in a row, we put a comma between the numbers. So those are some important things when we go to name it. So basically, when you go to name an alkane or really any organic molecule, for the most part, you always want to start with the longest carbon chain. That should correspond to one of the alkanes. You then want to find all your groups and figure out what those groups are called. And then you want to give the location of the groups again Smallest numbers is the preference. When we number things in organic chemistry, smallest is always sort of the preference to give things the smaller number. First off, any questions on that there? Now, when we looked at these earlier, this was C4H10. This is also C4H10. These are two things that have the same formula, but are connected differently. These are what are known as isomers of each other. And we actually do know that they are isomers because one way to actually figure out whether or not you drew an isomer, for example, is to name them. And if you come up with different names, then you actually drew different things. If you come up with the same name, you drew something different. Now, for example, if I had something like this, what should this be called? This is still butane, yes? Longest carbon chain is that whole thing. So even though it looks different, it is still butane, even though it's drawn differently. And sometimes people draw this and think that it's something different. So if you were going to name this, and obviously you named it properly, that's also butane. That is not an isomer. It's the same thing as this guy, just drawn differently. So a really good way, again, to determine if you actually did draw an isomer is to actually do that, name them and stuff. So when we look at these groups that are basically guys that are attached, as I mentioned, they will have one less hydrogen to allow them to attach. Here are some names. For example, our methyl group: ethyl, propyl, butyl, pentyl, and hexyl. Now, some groups do have special names, and it does depend on the type of carbon that is involved. And when we talk about carbons, we could actually classify carbons as either being primary, secondary, or a tertiary carbon. And let me just show you sort of the differences here, or what those are. So if we look at something like this, for example, when we look at the carbon that we want to identify as a primary, secondary, or tertiary carbon, what we're looking for is how many carbons are directly attached to it. So this has basically one carbon directly attached to it, and this would then be a primary carbon. If we looked at something like this, this carbon is directly attached to 1 and 2 carbons. This would be what is referred to as a secondary carbon. And a tertiary carbon would look maybe something like this. This carbon here is attached to 1, 2, and 3 carbons, and that would be known as a tertiary carbon. So I personally like to count carbons to carbons. Some people will be taught to count how many hydrogens are attached there. But if you count carbons, it's actually the same number. So 1 carbon attached is primary, 2 carbons attached is secondary, and 3 carbons attached is tertiary. If you count hydrogens, it's opposite. 3 hydrogens is primary, 2 is secondary, and 1 is tertiary. So sometimes people will be taught to count the hydrogens versus the carbons to carbons, but carbons is just easier. So what do I mean by that? If we take our propyl group here, which is basically our 3 carbons, right? And if we look at our propane, this carbon here is a primary carbon. It's attached to 1 other carbon directly. This carbon here is a primary carbon. So if you take off a hydrogen off of a primary carbon, you will get a propyl group. It's sometimes referred to as N-propyl, like normal propyl group. You just grab the hydrogen off the end. But There is also hydrogens here on this carbon, which is a secondary carbon. And if you grab a hydrogen off of there to allow it to attach, you will get a different type of group, which looks like this. And this is a very popular group where the attachment is going to actually be on the secondary carbon. And this is what is known as an isopropyl group. That kind of CH3, CH3 is an isopropyl sort of arrangement or iso arrangement. And that is known as isopropyl. That is why earlier when we looked at this guy here, this is 3 carbons in a row. 3 carbons in a row is based off of propane. This is an alcohol. Alcohol ends in OL. So this is what is known as propanol, OL, because it's an alcohol. And the OH group is at carbon number 1 and 2. And that is why this is referred to as 2-propanol. This is also referred to as isopropyl alcohol because that is the isopropyl group attached to an alcohol. And that's why it's sometimes referred to as an isopropyl alcohol. So isopropyl is a very common sort of group that's used a lot. And it's basically the difference is the attachment point on the propane is basically through the secondary carbon. Any questions on that there? Here are some other ones that again take advantage of some of that different connectivity. This is a sec-butyl, sec meaning secondary. Again, the attachment here is to a secondary carbon. That is T-butyl, which as you can see here, the attachments to a tertiary carbon. So some groups have some special names as well. Now, in terms of the halogens are named like we talked about with complex ions. So we have our FBrClI. That is our fluoral, bromo, chloral, iodo, just like we talked about with our transition metals. So they're named pretty much the same way. Again, like bromo, fluoral, iodo. So those halogens which do pop up are just basically named just kind of like normal. Any questions on that there? So if I look at, let's say we had a little line structure action, why not? All right. So let's say we have this line structure here and we wanted to basically name this thing. So the first thing that we want to do is look at how many carbons there should be, or is the longest carbon chain. So might as well just take the straight approach, which is 1, 2, 3, 4, 5, 6, and 7. So that looks pretty good. If we take here 1, 2, 3, 4, and go up, that's only 5. So that's obviously less. So that's not the longest. And your other option would be coming from the other end, would probably get you the same deal. 1, 2, 3, 4, and then up would be 5. So in this case, the longest carbon chain is going to be obviously our original there. Do this without erasing the picture. Perfect. So our longest continuous carbon chain in this case is, that was 7, correct? 1, 2, 3, 4, 5, 6, 7. So 7 carbons, all single bonded. That is going to be our friend heptane. That is basically the base of the name. Now, when we look at it, we actually have 2 groups that are there. We got this guy and we have this guy here, right? These are our 2 groups that are attached. So if I have a line with nothing on it, as we talked about earlier, a line with nothing on it really is a methyl group. It is a CH3 hanging out there, and that is a methyl group. I remember the line basically will have a carbon at the end and 3 hydrogens, right? And that right there would be your methyl group. Now, if we come over here, that is Br. That is a bromol group there. Br there. Any questions on that so far? So now when we go to number this guy, we do have two options. We could go left to right, which this would be carbon 1, this would be carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7. The other option would be we could go 1, 2, 3, 4, 5, 6, and 7. So if we go right to left, we will have groups at carbon number 4 and carbon number 6. If we numbered left to right, we will have groups at carbon number 2 and carbon number 4. It is as simple as 2 is less than 4. Yes. So the way that we would want to number this guy is going in this direction, as it gives the groups, in the case of alkanes, the smaller numbers. Any questions on that? Now, once we lock into place our numbering, we do not change it. We just keep it for everything. So I can get rid of the other way. So that means that we can now see that for our Br, it is at carbon number 2. So that's going to be like a 2- bromol. Our methyl is at carbon number 4. So that's going to be a 4- methyl. And that's pretty much our entire name. We just need to put it together here in alphabetical order. And again, it doesn't matter about the number. It is based on the name and no prefix either. So in this case, the bromine would come first. So this would be 2-bromol dash 4-methyl. And the base of our name is heptane. So that would be 2-bromol 4-methyl heptane in this case. Any questions on that name there? Between methyl and heptane, you do not know. So basically the dash is only when you're going from number to letter or letter to number, something like that. Yeah. So you don't traditionally need to put a dash there. Other questions? Okay, so let's take a look at a couple other naming type things. Now we saw our cycloalkanes like this, right? So let's just say I had something like this. So when we look at this, this is a cycloalkane, and that would be our longest continuous carbon chain. That is all the way through here, our ring basically. And our ring here again is based off of 6 carbons. A reminder that there is a carbon at each of these circles. You don't usually put the circles, but again, there is a carbon at each of those spots. So that's based off of 6 carbons, which is hexane. Because it's a ring type structure, this is cyclohexane. And now when we look at it in this particular case, we have just one group hanging out there, which is a line with nothing written on it, which we know is our methyl group, right? So this would be known as methyl cyclohexane. And now you may be asking, don't I need a number for that? And the answer here is this is what is referred to as being mono-substituted, which means there's only one thing on it. And because there's only one thing on it, you don't need a number, because wherever that thing is should always be carbon number 1 in this case. So because there's only one thing there, that should always be carbon number 1. It will be methyl cyclohexane. Just like if I drew it like this would also be methyl cyclohexane. It doesn't matter where that one thing is. Now, if you did have 2 things on there, like that, and let's just do like this, maybe. Now we do actually have two things on there, so we do need to give some numbers as to where things are located. Once again, the ring is going to be our longest continuous chain. So once again, the whole ring here is going to be it. And that is going to be, again, our cyclohexane, just like it was before. We again have a methyl group here. We also have a chloral group here. Now, in this particular case, we have two ways of numbering. We could go, or maybe a couple ways, but we could start with the chlorine and go 1 and go counterclockwise, 2, 3, 4, 5, and 6. We could also start with the chlorine and go clockwise, 1, 2, 3, 4, 5, and 6. So if we go counterclockwise, we'll go CC. We have groups at 1 and 2. If we go clockwise from chlorine, we have groups at 1 and 6. So clearly the better choice here starting at chlorine is 1 and 2 would be a much better move. We could also, if you wanted to, we could also, if you wanted to, start at the methyl group and number, which would give us 1, 2, 3, 4, 5, 6. Or start at the methyl group and go counterclockwise, 1, 2, 3, 4, 5, and 6. This is going to get us counterclockwise 1 and 6, and clockwise 1 and 2. Once again, starting at the methyl, 1 and 2 is a winner. So 1 and 2 is a winner. In this case, though, where should we start numbering, you think? We should actually start numbering, because it's a tie, right? 1 and 2, no matter which way you go. The next important thing is we put things in alphabetical order, which means since C is going to come before M in the naming, we might as well give this C the smaller number and start numbering there and go this way, 1, 2, 3, 4, 5, and 6. This will then give us a 1 chloral, 2 methyl cyclohexane. So if you have more than one thing kind of substitute on the ring, you do have to give numbers. You could go clockwise or counterclockwise. It doesn't matter. You could start at either one. It doesn't matter. So if you do have a distinction of which way is smaller, then you should go that way. But if it's a tie, no matter which one you start with, then you want to go alphabetically in terms of numbering. Any questions on that there? All right. So why don't you draw 3 isomers? We'll go with C5H12. So just draw 3 different structures that all have C5H12 in it and see what you come up with. And then name them. Let's see how you do. Okay, let's take a look and see. So we're going to draw some isomers here. So frankly, when you're going to draw something, you could just start with the carbons. It's the simplest thing to do. If you're just going to do line structure or even a condensed form, where you could just start with the basic carbons. And really, in this case, we are just looking to put hydrogens on, and everything else is hydrogen here. So we just want to put the right amount of hydrogens to get carbon to 4 bonds. Guy on the right has 1 line coming in, which means he has 1 bond. He'll need 3 hydrogens. Guy next to him has 2 lines, which means he'll need 2 hydrogens to get to 4. He'll need 2 hydrogens to get to 4. He'll need 2 hydrogens to get to 4. And he'll need 3 hydrogens to get to 4. And that would be the condensed formula for really our 5 carbons in a row, which is the easiest way to do it. We're going to do a little line structure on that one. It's just going to be a couple of zigzags till we have 5, and it will look something like that. Yeah. Now we're looking for isomers, which means we're really looking for different arrangements. So we could start with maybe instead of 5 in a row, maybe we'll shoot with just 4 in a row. And maybe we'll slap a carbon up this way. And that's 5 carbons. Again, everything else is going to be hydrogen. So again, guy on the far right there has 1 line. He'll need 3 to get to 4. This guy has 2 lines. He'll need 2 to get to 4. This guy actually has 3 lines, which means he should only have 1. This guy at the end here has 1 line, which means he needs 3 hydrogens. Guy up on top has 3 hydrogens needed, as has 1 line. That is 3, 6, 7, 8, 9, 10, 11, 12, right? So got 3, 6, 9. That was some bad counting there. 10, 12. And that is C5H12 as well. Yes. What's that? When you're drawing it? Yeah. Yeah, so when you're adding hydrogens, which is what you should do at the very end, after you put the carbons in, you just want to make sure carbon has 4 bonds. So you want to look at how many lines are going to that carbon, and then just add the appropriate number of hydrogens to get the 4. If we were going to line structure this one, it would be 4. And then coming off of our second one would be something like that. And it should look something like that there. Yeah. Any question on that one there? Now we could also maybe do this. Maybe 3 in a row and maybe put a couple carbons there. Now, if I did that, the guy on the right here would have 3 hydrogens. Guy in the middle actually has 4 bonds, so he doesn't get any hydrogens. Guy at the top will need 3. Guy at the bottom has 1 line, he'll need 3, and he will need 3. And there that will look. That again is 5 carbons and 12 hydrogens. We did a little line structure, a little bit like this maybe, and a little bit like that. Yeah, would basically look something like that. Now, I know we only did 3. Let's just do this one here just for fun's sake, shall we? We'll put 1 here. Again, sure. All right. All right, so we have 5 carbons in a row. Longest carbon chain obviously is 5, nothing else attached, no groups, so that's obviously pentane. Now, when we come to our second one here, longest carbon chain in this case is 4 across, right? You could also get 4 by going in this direction. So no matter which way you go, you're going to get 4 across here. And 4 across is butane. Now, in this case, we do have a group attached over here, and that is a 1 carbon group, which is our methyl group. Now, we do want to number this chain here, and we could go left to right, which is 1, 2, 3, 4. We could also go right to left, 1, 2, 3, 4. In this particular case, we should end up at this direction. And again, it's going to give the group the smallest number. And that number there is 2. And that means that this would be a 2-methyl group here. And if we put that together in our name, this would be 2-methyl butane. So is the first guy I drew and the second guy I drew, are they isomers of each other? The answer is yes. They are different names, right? They don't have the same name or anything like that. So if we come to the third one here, longest carbon chain going to be 1, 2, 3. You could also get 3 going this way, and you could also get 3 going straight up as well. So it doesn't matter which way you choose, it all should come out the same. And this case, 3 carbons in a row is propane. We have a group here and a group here. That is a methyl group. That is a methyl group. In this particular case, we have 2 of the same group in this particular molecule. And whenever you have 2 or more of the same group, you actually use prefixes. And in this case, the prefix di for 2, tri for 3, tetra for 4. So in this case, there's 2 methyl groups. This is going to give us a dimethyl situation happening. And we do need to give the number of these groups. And we could go 1, 2, 3. Or we could go right to left, 1, 2, and 3. And in this case, it doesn't really matter which way you go. They both are going to give those methyl groups carbon number 2. Now, because they are on the same carbon, you still have to give the number twice. And this would be a situation where we would have 2, 2. And again, each 2 is for one methyl group that is present. And putting that together here, where everything falls off here, that's going to be a 2, 2 dimethyl propane, which is obviously this guy here. Yeah. Now, the di is not because, by the way, the di is not because they are on the same carbon. It's just because they're in the same compound. If they were on different carbons, you would still call it dimethyl. So, it doesn't matter. But the di is because there's 2 in them, or if you have 3 of the same, it'd be tri. That is a different name than the other 2 that we had, which means all 3 of these are isomers, right? Now let's take a look at the last one that I drew for fun. Wow. Longest carbon chain on this one is still 4 in this case. This is going to still be known as butane. When I number this is carbon 1, carbon 2, carbon 3, carbon 4. Going the other way, 1, 2, 3, and 4. The way I should number that's going to give my methyl group the smallest number is left or right to left. So that is the way that we want to number. And that would mean that this is 2-methyl butane. Now, is this another isomer? This is not, because that is the exact same thing as this one. It's just drawn differently. So although it is that, it's just turned around, so it's not an isomer. So that's why when you're going to draw isomers, for example, the best thing to do is to draw them and name them properly. And if you find yourself with 2 of the same names, it means you just drew it differently, and they're not really isomers. But if you name them correctly and you do end up with different names, then they are going to be isomers. Any questions on any of those there? Let's just talk about here if I did have a name like 3-chloral 4-ethyl hexane. And let's say I wanted to draw this. So this is probably the easiest thing to do, is to actually draw it if you're given the name. And whenever you're given a name and you want to draw something, it is always smart to start backwards in the name. And when we look at the name hexane, that tells us how many carbons we should lay down, and that should be 6, right? And that would be all I would start with, is just the carbons. 2, 3, 4, 5, 6. That takes care of this part of the name. Now, we have a ethyl group at carbon 4 and a chloral group at carbon 3. The nice thing about you drawing it is this: because you're drawing it, you could call the guy on the left here carbon 1, or if you wanted to, you could call the guy on the right carbon 1. It doesn't matter, whichever way you want to go it. Whichever way you choose, you do need to keep that numbering. So for me, I'm going to start on the left here and call this carbon number 1. And that means for me at carbon number 4, which would be here, I should have an ethyl group, which is actually based off of ethane, which is 2 carbons. That takes care of that. And at carbon number 3, which for me would be here, I have a chlorine, which would be that. And pretty much everything else here, it's just going to be hydrogens to get to 4. So this guy will need 3. This guy will need 2. This guy will need 1. This will need 2. That will need 3. This guy will need 1. This guy will need 2. This guy will need 3 in this particular case. And there it is. That is the condensed formula for what we just did. If you're going to do the line structure, you would do the same thing. You would start with 6 carbons. 1, 2, 3, 4, 5, and 6. And you could do the same thing if you want to call this guy carbon number 1. Then for this at carbon number 4, 1, 2, 3, 4, we would have a 2 carbon group. And at carbon number 3, we would have our chlorine. So it looks something like that. And you would have your line structure done. So going from name to formula is not too bad. You usually just kind of work your way backwards in that case. Any questions on that there? All right. Why don't we take a 10-minute break so my head doesn't hurt anymore, and we'll come back to you a few more examples. Okay, so we're going to continue on here. And we've been talking about naming and drawing some of these alkanes. So just to, again, go through the steps here as we talked about, you always want to look for the longest continuous carbon chain. As I mentioned before, the only real rule is you can't go backwards. So you got to go one way until you hit a dead end. You do want to check all the possible options because sometimes, again, the kind of straightest one is not always the longest carbon chain. Again, it can kind of go up and over and stuff like that. So again, as you can see here, this one is the straightest, but the longest is this way, can go up and over. So you do want to make sure you check all of your options. Again, the number of carbons in that chain will probably correspond to an alkane name, and that really be sort of like your base number of the name. You also want to identify any groups that are attached, like we talked about. And in terms of alkanes, the groups you take the priority in terms of numbering. And we want to number the longest carbon chain, again, whichever way gives the groups the smaller number. That is always what we're looking for here. We do want to name what groups are there. They could be alkyl groups like our methyl, ethyl, propyl groups. They could be a halogen like bromo, chloral, iodo. And we do want to give the number of where they're located. So that's really what the name's all about, sort of telling people where they can find these different groups on this chain. As we saw in that one example, and as I mentioned, if you happen to have more than one of the same group within a molecule, we do use prefixes like di, tri, or tetra. Once again, they do not need to be on the same carbons, but they just need to be in the same compound. So if you have 3 methyls on different carbons, then it would be trimethyl. You do still need to give the number for each of the locations of those groups. So if you did have like a trimethyl situation, you should have 3 numbers to go with that. And again, you would separate the numbers by comma if they're numbers to numbers. So here, as we saw here, we have a methyl group there and a methyl group there. That's going to give us our dimethyl part of this, and it would be a 2, 3 dimethyl because of the location of where those groups are located at. We do put the groups in alphabetical order, ignoring prefixes. So again, we do go alphabetical regardless of prefix. Also, we go alphabetical regardless of number. So something could have a larger number but start alphabetically lower. That guy would come first. So number wise, it doesn't really matter. We do go by that alphabetical. As we talked about, the other major sort of considerations, a number and a letter, that's going to be a dash. And again, a couple of numbers there, that's going to be a comma between the two. So if we look at this guy again, longest carbon chain, pretty much straight across. That is 1, 2, 3, 4, 5, 6. So that's going to be hexane. We have a methyl group that's attached. And you could probably just see going left to right will give that methyl the smaller number. So that's going to be our 2-methyl hexane, all one word, a big space there, but no dash there needed in that case. Here, again, we would look for the longest carbon chain. Straight across is probably going to work. 1, 2, 3, 4, 5, 6. Your other option would be 1, 2, 3, 4, 5, 6. Your other option would be 1, 2, 3, 4, which is less. So you do have a couple of ways to which you could get to 6. Again, if you do have that option of going kind of the straighter one, is probably a good one to look at because it makes you able to kind of see other things a little bit easier. And again, here we obviously have our methyl groups that we saw. So we have 2 methyl groups is going to give us a dimethyl. Going left to right here, 1, 2, 3, obviously is going to give us smaller numbers than going in this direction. So that direction is not going to work. And that would give us 2, 3 dimethyl for the locations of those guys. And then the 6 carbons would give us hexane in this case. Any questions on that one there? Now, this one, we got a lot going on. So if we just go straight across here, let's see what we got going. We got 1, 2, 3, 4, 5, 6, 7, 8 carbons. If we went straight across, 1, 2, 3, 4, 5, 6, 7. So that is less carbons. Other option may be 1, 2, 3, 4, 5, 6, 7, 8. Does look like 8 is a winner no matter kind of which way you go, I think. So I think we had an 8 that was more straight there. So we do have 1, 2, 3, 4, 5, 6, 7, 8. So the base of the name here is going to be octane because of the 8 carbons. We do have a few groups kind of hanging off here. We got a methyl there. We also have a methyl there. And we have a 2-carbon group, which is based off of ethane, and that would be an ethyl. Numbering this, if we go left to right, 1, 2, 3, 4, 5, 6, 7, and 8. That would give us groups going at 2, 5, and 6. If we went in the other direction, 1, 2, 3, 4, 5, 6, 7, and 8. We would have groups at carbon number, looks like 3, 4, and 7. So we are going to go this way as it is 2 is less than 3. So we would want a number in this direction. Doing so means that we do have a 2, 6 dimethyl groups happening. We also have a 5 ethyl. Here we do go alphabetical regardless of prefix. So what we are comparing in this particular case is our E to our M. So it should be the E that comes first. So that's going to be a 5 ethyl, 2, 6 dimethyl, and a little octane action there. on the back end there. Any questions on that naming there? Let's see if they agree. Hopefully they do. That'd be good. 5-ethyl 2,6-dimethyl-octane. Perfect. All right, so why don't you try some here for fun? Why not? Let's do it. Not sure how much fun it is, but let's try it anyway. These are 3 different ones here, I think. All right, give the names for each of these guys. Top guy, left guy. All right, let's take a look, see how you're doing. We'll start with the top one. Again, we want to find the longest carbon chain. Might as well start just going straight across. 1, 2, 3, 4, 5, 6. We also could go 1, 2, 3, 4, 5, which is less. We could go 1, 2, 3, 4, 5, 6, and we could also go 6 that way as well. So there's a couple different ways, but looks like perhaps 6 is a winning number there. So that's going to be our main chain there, which is 6. So we do know that really the base of our name is going to be hexane, as they're all single bonded. We do have this group right there, which we know is a methyl group. We have this 2-carbon group, which is based off of ethane, which is an ethyl group. So we do want to number this to give the groups a smaller number. And just looking at it, perhaps you could tell that going right to left will do that. That's a 1, 2, 3, 4, 5, and 6. Again, if we go the other way, our first guy is not going to be the carbon number 3, so obviously 2 is less than that. That would mean that this would really be a 2-methyl, and that would be a 4-ethyl. Once again, if you went in the other direction, you would end up with 3 and 5, which obviously, again, is larger numbers. So putting that together, alphabetical here, we're going to go with a 4-ethyl, 2-methyl, and a little hexane at the end there. Yeah. Any question on that name there? Looking at the one to the left on the bottom, longest carbon chain, perhaps 1, 2, 3, 4, 5, 6, 7. I think that's going to probably win. I think your other option would be 1, 2, 3, 4, 5, which obviously is less, and 1, 2, 3, 4, which is less as well. So that looks like a winner there. And 7 is going to be heptane as the base of the name. In this case, that would mean we just have one group left over, and that's a 1-carbon group, which is going to be our methyl group. And numbering this looks like 1, 2, 3 would work. Again, going in this direction is going to be more than 3, so that would be 3-methyl. And putting that together would give us 3-methyl heptane. Any questions on that one there? Longest carbon chain on the one on the right is how many? It is 8. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. And the one that you do want to go with, though, is neither of those, because you could go 1, 2, 3, 4, 5, 6, 7, and 8 going in that direction there will give us our longest carbon chain. That's going to give us 8, which means we got an octane happening there. In terms of groups here, we would have this group here, which is a methyl. We have this 2-carbon group here, which is an ethyl. Now, in terms of numbering, we go this way, 1, 2, 3, 4, 5, 6, 7, and 8. That gives us a group at carbon number 3 and 5. We want the other way, which would be 1, 2, 3, 4, 5, 6, 7, and 8. We would have a group at 4 and 6, which is too large. So we do want to go the other way there. They give us a smaller numbering, which was way. That means in this particular case, we got a 3-methyl and a 5-ethyl. Again, E would come first, even though the number is larger. So 5-ethyl, 3-methyl octane. Any questions on any of those names there? All right, let's take a look here. All right, why don't you draw some formulas? Why don't you draw the condensed formula? Why don't you also do the line structure for this guys as well? Let's see what you come up with. Okay, let's take a look here. So once again, if you have the name, we always want to work backwards. So the last part of name, which is butane, tells us really how many carbons, and that should be 4. And again, if you're just going to do condensed, you could just do the basic just carbons. That takes care really of that. 2,3 dimethyl. Dimethyl means there's 2 methyl groups. The 2 and the 3 means there are carbon 2 and carbon 3. And since you're drawing it, I'm going to call this one carbon number 1 for me, which means right here would be carbon number 2 where there's a methyl group, and right next door would be carbon number 3 where there's a methyl group. And the rest here is just going to be hydrogen to get us to 4 bonds. So 3 there. This guy has 3 bonds already, so just needs 1. He's got 3 bonds, just needs 1. And we just need 3. Again, if we did a little line structure on this here, it looks something like that, and a little like that type of deal. Any questions on that there? All right. So same thing here. We're going to work backwards. Heptane is 7. We'll go 7. 1, 2, 3, 4, 5, 6, and a 7. I'm going to call this carbon number 1 for me. You could do the other side if you wanted to. That means at carbon number 3, there's an ethyl group. So there should be a 2-carbon group there. And at carbon number 2, there's a methyl group, which would be a 1-carbon group. And then we could really fill in our hydrogens. We will need 3 plus you need 2, 2, 2, and just 1 there, 2 there, 3 there, 1 there, and a 3-pack there. For our line structure, you could do the same thing. Just start with the 7. 1, 2, 3, 4, 5, 6, 7. And again, you could go, this is say carbon number 1 right there. We'll go to carbon number 2, a methyl group, which should be a line. And carbon number 3, there's like an ethyl group sort of happening there. Any questions on that there? All right. Lastly, we have pentane, which means we should have 5 carbons. 2-chloral, I'm again going to call that carbon number 1. So 2 would be here. There should be a chlorine. And at carbon number 4 for me would be here. There's a methyl. Rest is just going to be hydrogens to get the 4. And same thing with the line structure. I would start with the 5 carbons, go to carbon number 2. You do need to write the Cl, otherwise it's a methyl group if you just put a line. And at carbon number 4, that should be just a line like so. Any questions on drawing those things out? To me, I think it's the easiest thing to do because you just draw what it says. Basically, it tells you what to draw. Any questions? What was that? No, I'm just going to give you like naming, just nonstop naming, like 300 questions of organic compounds. Name this molecule, name this one. I'm going to take this really big book over here and just copy all the pictures in there and go, give me the name of everything in there. All right. All right, so I'm reaching my organic limit here. So we're gonna finish here with we're gonna finish here with a couple of types of reactions that some of these alkanes undergo, just to finish it up. Too much organic, I have flashback, and it's not good. It's not a good flashback either. All right, so alkanes, like normal organic compounds, can actually do a combustion reaction, which you should be familiar with. So if you took something like an organic guy, which again is your carbons, hydrogens, and oxygens, react it with a little bit of oxygen, you get a little CO2 and water produced in a combustion reaction, usually also flame in a lot of cases, like if you took methane, right, which is like what happens when you light a Bunsen burner. A little CO2 and water in this case, a little 2 there, 4, a little 2 there to balance it. Now, in organic chemistry, there's different types of reactions that happen. And if you take organic chemistry, you will learn the mechanisms of these reactions, which means you'll be drawing a lot of arrows for electrons. They are so specific that if you draw an arrow like this, it may be marked wrong because you're only moving 1 electron. So you should just do one little arrow like that. That's how it gets. So you'll learn about the mechanism. It's clear we're not going to talk about how every bond breaks, where things shifts and everything. But there's several different types of reactions in organic chemistry. There's substitution reactions. There's addition reactions. There's elimination reactions. Elimination reactions. There you go. And there's a bunch of types of reactions that occur. So alkanes will kind of do a substitution reaction. And in a substitution reaction, what happens is, for the most part, they substitute a hydrogen. Gets substituted for. So if you do this and maybe you add like a bromine, Br2. So this is basically Br2 here, right? So what happens is one of these hydrogens in a mono-substituted situation will come off, and one of these guys will go on in its place. So they basically swap places. And the result of that is you get pretty much everything exactly the same. And you'll get a Br. Now you do have an H that came off and an extra Br, which could come together and make HBr as well. So you could actually substitute out any of the hydrogens and you'll get this sort of reaction that occurs. It could also occur on a cycloalkane, same deal. Say Cl2, for example. Although not drawn here, there are 2 hydrogens, for example. So it could come off, it could come on, and you'll end up with basically a chlorine there. Too many else. Chlorine plus an HCl that will come out. So alkanes will typically do these substitution reactions, and that is different than, say, an addition reaction, which you oftentimes will see with alkenes. So just to really finish up on that, alkenes, just to show you the difference between them. Alkenes are those guys that have the carbon-carbon double bond. And when we take something like a alkene, and we add something to it, like, say, hydrogen, which is very common, H2. This is what is sometimes referred to as a hydrogenation reaction. Also, like if you ever heard somebody say this thing is partially hydrogenated, this is how they move like oil to margarine and that type of stuff. What happens is in this particular case is both of these things get added on to the double bond. But clearly at this point, each carbon in that double bond is full. It has basically 4 bonds, right? So it can't take any more. So when this process happens, basically this guy becomes a single bond and nothing else really changes. So this guy just becomes a single bond. And what that then allows is for each of these hydrogens to be added on. And they're actually added on, and I'll draw them as blue guys. they're added on here, one to each of the carbons. So this is what's known as an addition reaction. It's known as a symmetrical addition because you're adding two of the same thing. You can't screw it up, hopefully. They go on opposite carbons. You break the double bond to make room, and it does that. You could do that with like Br2, for example, if you had the same thing. What would happen is your double bond would become a single bond. Everything would still be there exactly the way it was. And then each of these guys would get a bromine that happens. So this is a way, for example, you could go from an alkene to an alkane. You could do a hydrogenation reaction and add hydrogen to it. By the way, this is also, for example, I'll draw up hydrogens. H, 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 H. If you added something like an alcohol here, I'm sorry, a water, an alcohol. If you added water, which is H2O, water will actually add as OH and H, and it will still happen here at the double bond. And in this particular case, our double bond will become a single bond. Everything else stays exactly the same, which is a really good thing to remember when you're drawing these type of reactions. People think all kinds of weird things happen. In most cases, they don't. And basically, the hydrogen goes to one. And in this case, the hydrogen will actually go here. And the OH will go to the other. And that is how you go from an alkene to an alcohol. That is 2-propanol isopropyl alcohol. So that's how you can make something like isopropyl alcohol, also an addition reaction. This is what's referred to sometimes as an unsymmetrical addition because the two things you're adding are different. You're adding an H and an OH rather than in the first one, you're adding two H's or two Brs and stuff like that. So there's all kinds of different reactions that occur in organic chemistry. There's also our favorite oxidation and reduction reactions, where if you took something like a alcohol such as this. This is what is known as ethanol, based off of two carbons and an alcohol group there. So based off of two carbons, ethane, alcohol, OL, so that is ethanol. If you oxidize it, send it through an oxidation reaction. One of the definitions of oxidation that we talked about is the loss of hydrogen. What happens in this reaction is hydrogen here goes away, hydrogen here goes away, and you actually make a double bond between those two. So you're not short a bond. And you just made another organic group, which is known as an aldehyde. And that's a primary alcohol. Will actually make an aldehyde if you oxidize it. By the way, if you go the other way, that is the reduction reaction, where you add the hydrogen back into those two spots, and you'll end up with your hydrogen back on, going in the opposite direction. So there's oxidation and reduction reactions in organic chemistry a lot, and they deal with those other definitions that we talked about when we talked about redox: gaining hydrogen, losing hydrogen, gaining oxygen, losing oxygen. For example, if you took this guy one more time and you oxidized it, it will actually then gain oxygen right about there. And this makes another organic guy, which is known as a carboxylic acid. And the only difference is it inserted oxygen right there from where it started. And that's, again, another definition of oxidation. So in organic chemistry, there's all these different types of reactions that occur. And like I said, if you take organic, you'll learn about the mechanisms of those things, what bonds are broken, where the electrons go to allow these things to occur. And that is fun. Any questions on that there? All right. I feel like that